And grace period's over. All right, so welcome to our second virtual session for chemistry. I know last week we didn't have one because of the field trip that I was on, but we're going to be continuing with the same type of math stuff that we didn't quite finish in the first virtual session. So just to recap a little bit about what we did in the first session, which if you missed that one, there is a video and a link to this PowerPoint posted in the last part of modules, which I will show you. Actually, I'll just show you now because it is a helpful thing to know. So in the chemistry course, if you go to modules and you scroll all the way down, you'll see, you won't be able to see any of these because these are all virtual sessions that are coming up in the future. But you'll see just this first one, which I did not retitle because it was not about energy and temperature. So we'll just fix that real quick. Let's see, edit. Unit conversions. Okay, so this is where all virtual session information will be, right? So if you ever miss a virtual session or you need to go back and look at something that we went over, this very last module, eventually there will be many published, right, as we go through the whole year. And remember, my goal in these virtual sessions is to show you shortcuts or go over math or go over some of the hardest parts of the course. So if you are struggling with something, it's helpful if you let me know, because I do create these virtual sessions around what you guys are either not doing well on or are confused on. So last time we talked a little bit about the virtual session norms, right? Having your camera on, participating, asking questions, being respectful, blah, 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 blah. We did some converting of kilograms to grams. We talked about the metric conversion chart, moving the decimal, because the metric system is based on units of 10, so you can easily convert between the metric system. If you missed that in the first virtual session, go watch the video. We started doing some dimensional analysis about converting different units to other units. And then we started working on this question, which I believe, found an answer to this, but this is kind of where we left off. So right now, as a warm-up question, you're going to need a calculator for this. So you're welcome to use a phone calculator or your computer calculator, but go ahead and get your calculator ready. If you have a physical calculator, that's also fine. I want you to, even though I have a setup here, so we'll pretend that I don't, I want you to read this question and see if you understand the setup and actually do the calculation to figure out how many dollars were found and to continue doing this, finding the weight in kilograms. So this question says, you find a lot of pennies. How many dollars did you find? If each penny weighs 0.01 grams, how much do your pennies weigh in kilograms? So I'm going to give you guys probably about 2 minutes right now. I want you to either work on solving this or continuing to set up for how much those pennies will weigh. Sorry, I'm making a lot of noise. I'm getting out my own paper because I like to write these on paper sometimes too. So if you are finding an answer for either one of these questions, how many dollars you found or how much the pennies weigh, feel free to pop an answer into the chat if you do have one. Otherwise, I'm going to give you guys probably about 45 more seconds and we're going to start going over this. Thank you, Logan. That is also exactly what I got. So we're going to start going over this really quick. Logan has provided us with both correct answers, right? This first part isn't too hard to set up. And remember, the key in any of these questions is getting your units to cancel so that you're left with the units that you want. So in this case, we started off by taking the information that we know, which is how many pennies we have. Okay, sorry about that, guys. Our internet just went out here, which is really rare and random. But anyways, I'm back. So in the middle of whatever I was saying, I have no idea what I was talking about when that happened. I was like, what happened to my Zoom? We start with what we know, right? Which is how many pennies we have. And then we start to either come up with conversions we know or look in the question to see if they gave us any conversions. Well, we are looking for dollars and we do know how many pennies are in a dollar, right? And if you weren't sure, you could always look that up. 100 pennies are in a dollar, right? So in this case, all we're going to do is take our number of pennies and divide by 100, and we get the answer that Logan suggested to us here, which is $134,061.09, right? So in this case, since we are talking about a dollar amount, right, the dollars become our units. You cannot see blue on this. Dollars become our units, right? And if we're in dollars or money, we're always going to report significant figures that represent that, right? So in this case, you would include the 0.09 because that is realistic to represent dollars, right? You wouldn't put 0.099998, for example, right? Because that is not how we would represent money, just in case we had extra units, but we don't. So again, just to reiterate, you should be able to cross out those units, right? Pennies cancel, and we're left with dollars, which is exactly what we want. Now, the second part of this question, how to set it up. It's pretty similar in concept. We are going to start with the pennies again, right? How many pennies we have. That's something that we know that was given to us in the question. And we will do what? What would be the next step here in terms of things that we know? What else do we know about converting from pennies to mass here? What does the question tell us about how much 1 penny weighs? Thank you, Oliver. 1 penny is 0.01 grams. So that is a conversion factor. We can place those in any order, right? We're saying that 1 penny is equal to 0.01 grams. We could also say 0.01 grams is equal to 1 penny, right? Those are interchangeable because they're equal. That's like some math property stuff right there. So what that means is that in this case, we want pennies to cancel out, right? We want to know weight here. So we're going to be putting pennies on the bottom, and we know that for 1 penny, penny is a hard word to type for me for some reason, we have 0.01 grams. Again, that was a conversion given to us in the question, right? That's not something that we would necessarily know. Okay, so now we're in grams. Well, they want to know how much the pennies weigh in kilograms. So we need a conversion between grams and kilograms. We could always refer back to our metric system chart, right? You could also Google that if you're not sure. You could use two types of conversions here. I usually like to do 1,000 grams to 1 kilogram as my conversion. However, you could also do 0.001 kilograms are in 1 gram, right? Because those are the same thing. But in this case, it's nice and easy to divide by 1,000, in my mind at least. So now we do a little check. Are we in the correct units? Well, pennies will cancel, right? Because plural and singular, same thing. Grams will cancel. And we're going to be left with kilograms, which is what we want. And if you go ahead and do this math out, then you should get 134.06 kilograms for the weight of the pennies. Okay. So that should be a little bit of a review of what we did last virtual session. Also, just helping you make sure you're understanding this dimensional analysis. Again, like I said before, this stuff is going to come back over and over and over and over and over. So let's move on to the next one. Okay, so if a movie ticket costs $8.50, how many movie tickets can you buy with your pennies? So remember that dollar amount that we got in the previous question was 134,061.09 was our dollar amount that we figured out before. So knowing that, how many movie tickets can we buy? Well, let's set this up together. So what do we know to start? Well, we know how much money we have, right? Kind of. At least we vaguely know because we just solved for it. We hope it's correct, right? It's correct. So we know that we're starting with 134,061.09. That's how much money we have. $134,000, which, by the way, no one is commenting on how many pennies this is. That's insane. Can you imagine counting all of those pennies? I would have lost my mind. I would have given up and just been like, I'm rich, I have a lot of money. So we have a dollar amount here, and we have another conversion factor. This one, in your mind, if you're good at math, you might have just been thinking, well, you're going to divide by $8.50, right? And that's going to tell you how many movie tickets you are going to have, which is true, right? That's exactly what we're going to do. However, we want to represent this as dimensional analysis, because later on, you're going to have complicated problems with so many steps that if you start trying to think about what you're dividing and multiplying by, there's a huge chance you will make mistakes. So to set up our conversion factor, we're going to say that for every $8.50, you end up getting 1 movie ticket. And that's just a way to have a conversion. And remember, these boxes represent multiplication, right? So it's implied that right here, we are multiplying between these boxes. It's just the easiest way to represent this on the computer. So in this case, if we divide $134,061.09 by $8.50, how many movie tickets can we get? What do you guys get as the answer for that? Thank you, Logan. 15,771 movie tickets, right? And this brings up a good point too, that in this case, we're talking about movie tickets, so we would not report half a ticket, right? We're not gonna say, and you can buy 0.333 of a ticket, right? It wouldn't make sense there. So in this case, we would make this a whole number, rounding down, right, to the amount of movie tickets that you can actually get. Okay, so that one again, really I kept that in there because I want you to see that dimensional analysis can be applied even to just a one-step, really simple division question, but it will help you see multi-step problems easier if you set them up like this, right? It's gonna save you a headache later on, essentially, is why I'm focusing on it. Okay, so next slide here, I gotta get rid of the money. We don't need that anymore, right? A lot of technology to manage. Okay, there we go. So now you're going to try by yourself to convert 1,000 meters per year to kilometers per second. So working to set up your own dimensional analysis here. Again, dimensional analysis is the box thing that will convert meters per year into kilometers per second. So I'm going to give you guys about a minute to try this on your own, then we'll go through how to set this up. Looks like I'm going to need a lot more boxes if I do this step by step at least. Okay, so I'm going to go ahead and start setting this up. If you are still working on this, feel free to keep going. However, I am taking it from only Logan giving me answers in the chat that other people are probably still a little confused. Right? Practice makes perfect on these. It's going to be possibly something that takes you a while to get, but once you get it, it's a pattern. So just like every other question, I'm going to start off with writing what I know. They told me that 1,000 meters are per 1 year, right? That's the first thing I'm starting with. It says per year, and I put the 1 there, right? I like to put the 1 to know that that is representing 1 year. It's an implied 1. So what I chose to do first was convert years to seconds. Now, you could have looked up how many seconds are in a year. That's totally fine, but let's say that you don't have the opportunity to do that, right? Or you want to know how to do this the long way. You break it down, right? How many days are in 1 year? $365. Good. How many hours are in a day? Give or take a quarter, exactly. How many hours are in 1 day? 24 hours. How many minutes are in an hour? 60 minutes. How many seconds are in a minute? So that was a lot of math, right? You might have been able to, again, skip that if you happened to know or you looked up how many seconds were in a year. Notice the units, right? Years are canceling. Days are canceling. Hours are canceling. Minutes are canceling. We're left with seconds. It's in the denominator. That's exactly what we want. Now, meters to kilometers. How many meters are in a kilometer? 1,000, right? Again, if you're not sure about that, you can always look it up. You can use the metric system to do that, right? Some of these you're just going to remember. Like kilometer to meter, kilogram to gram, those are relationships that you're going to see over and over and over. You just kind of learn them eventually. Okay, so now I want to make sure my meters are going to cancel. That's why I put meters on the bottom so that I'm left with kilometer seconds. I personally really just enjoy crossing units off because it makes me really positive that I did this correctly, and I like to cross stuff off, right? Not a necessary step, but regardless, all my units are canceling so beautifully, including my meters, to where I'm left with kilometer seconds. So then now if we do out this math, what do we get as our answer? And if you're stuck on how to put this into a calculator, right, or how to do this math, you're basically going to multiply by everything on the top and then divide by everything on the bottom. You can do it one at a time if you want, or you can just go straight across on the top, straight across on the bottom. That's what I personally like to do. So in this case, it would be 1,000 times 1 times 1 times 1 times 1 times 1 times 1, right, which is going to be 1,000. And then I will divide 1,000 by 365, and again by 24, and by 60, and by 60 again, and then by 1,000. So you should have gotten a very tiny answer. In fact, 1, 2, 8. I got 3. If I could figure out how to get out of my Zoom here. I got 3.0 times 10 to the negative 8, right? In other words, 0.000000003. So there are 7 zeros in front of that 3. So it should be a really small number that you get here. Again, that would make sense, right? We're going from something, a meter, which is part of a kilometer, right? We already knew 1,000 meters is 1 kilometer. And then we're going from a big time to a small time. So it would make sense that we get a tiny answer here. Any questions on the setup of this, how to do this? Do you want me to repeat something? Remember, this is time for you to ask questions, right? As I already know how to do these questions, so this is your time. So if you want me to talk about it again or repeat it, I don't mind, right? I'm not going to be upset. If you want me to say it 8 times, I will. Usually I do that on important things. In fact, someone wrote that on a test recently. They were like, I picked this answer because you said that about 4 times in the virtual session. I was like, well, that's true. I do emphasize. Okay, so our next one is going to introduce another concept here, which is a squared unit, right? So does everybody know what that little caret means? I hope so. I have it here in my answer that I just wrote as well, right? It's representing that that's an exponent. You can, of course, write in a real superscript and have it look like a real exponent, but that I find really time consuming, so I usually do the caret. So in this case, we're saying a tiny piece of metal can support 4 kilograms per meter squared. Convert to grams per kilometer squared. So this is another conversion question. Type a 1 in the chat if you'd like to try this one by yourself. Type a 2 in the chat if you'd like for me to show you how to set this up and you just follow along. Ooh, we got 2 1s and a 2. We're 50-50. Okay, so if you want to try this question by yourself, this is going to sound weird, but just mute the computer for a second and try it, right? And I'm going to set it up for the 2 people who'd like to see it set up, and then we can confer at the end and see what happened. So keep kind of looking over at your computer to make sure that I didn't move on without you, right? But if you want to mute me or turn me down for a second, that is fine. Otherwise, we're going to get started with setting this up for those who would like to see how I would set this up. Insert table. Okay. So, just like all the other questions, we're going to start off with what we know. We're given that we have 4 kilograms per 1 meter squared. Well, where do we want to start? Do you guys want to start with kilograms or with meters squared? Which one of those seems easier to convert? I agree with Chris. Kilograms doesn't have any squares. Let's start there, right? So how many kilograms are in a gram, or vice versa? How many grams are in a kilogram? Yes. We just saw this one before, right? We know that there's 1,000 grams in 1 kilogram. That's a conversion that we know. There's no reason that you can't just keep using the one you know, right? So you can say 1 kilogram on the bottom, oops, type it in the chat instead of here, is 1,000 grams. Okay, well, we want to get to grams. This would allow us to cancel kilograms. That seems like a good step, right? Alternatively, you could have also said 0.001 kilograms is equal to 1 gram. Again, that's going to be the same exact math. So it really doesn't matter which one you do. I like to pick bigger numbers personally rather than decimals. That's my personal preference. So we're good on kilograms. Now we need to talk about meters. So what does it mean when we are squaring something? I'll repeat the question. Okay, or maybe not, because Logan probably already solved the question and he's back here to help. Yeah, you're multiplying a number by itself. So the same thing goes for a unit, right? 1 meter squared, we're basically saying 1 meter times 1 meter is 1 meter squared. So we have to keep that in mind. When we convert, we have to square our conversions as well, or cube them, or whatever, right? Any exponent you have has to be applied to your units as well. So in this case, we've already converted grams. Meters, we want to go to kilometers. So guess what? It's the same nice, easy 1,000 conversion here. We know that there are 1,000 meters in 1 kilometer. Now, that is not squared. So you could, depending on how you like to notate this, right? I personally usually just put this whole thing in parentheses like this and put a squared around it. You could also just put it twice. So you could do it like this, right? If that makes sense to you, or you know that you have to square that number, you have to multiply it by itself. So you could actually just put the same exact conversion again, 1,000 meters per 1 kilometer. Because now we're basically separating out a squared number, right? And that would give us kilometers squared, right? Because kilometer times kilometer will be kilometer squared. It will give us meters squared on the top, which will cancel out with our meters squared on the bottom. So when you see these squared, you might even sometimes see cubed, right? If you're talking about volume, for example, like volume of a cube, trying to convert between that, you have to account for the squaring in your math. Otherwise, you will be off, usually by, in this case, you would have been off by 1,000, right? So a pretty big deal. So then if we multiply all of these things out and divide, we get 4 times 1,000 times 1,000 times 1,000, and we get a huge number, right? We get 4 times 10 to the 9th. 4 times 10 to the 9th power. And again, that means that there are 9 zeros after that 4. So it's quite a large number, which would make sense, right? Because in this case, we're multiplying by 1,000 3 times. It's going to be pretty big. If this meter squared number over here had been bigger, then we might not have had such a big number, right? Or 4 billion. Thank you, Logan. Yeah, actually, that's an even easier way to say it. Instead of 4 times 10 to the 9th, you could say 4 billion, which is also correct. So that's the trick on the squares, is that you do have to square your conversion. We didn't square the grams, right? Because we didn't need to. Kilograms wasn't squared, just the meters was. So we had to sort of break that apart. There's one other helpful conversion that I will tell you about really quick, which is that 1 milliliter is equal to 1 centimeter cubed. That is a helpful conversion to know. Probably won't come up until much later in the class, right? But those are both measures of volume. However, centimeters is cubed, milliliters is not. That can be helpful sometimes when you're converting to quickly go between liters and meters, any versions of those, right? Centi, killi, whatever. Kilo, I mean kilo, ugh, can't speak. So that's a helpful conversion to know that does involve this concept of cubing, right, instead of squaring. So just be on the lookout for questions like that because they kind of sneak up, and if you first encounter one and you haven't thought about it, you might not know to square that conversion. Okay, moving on. So now we're going to talk about moles. I know it's a lot of like random stuff in this virtual session, but honestly, it's random stuff that's going to help you be successful in the class. So the first thing that we're going to do is we're going to talk about molar mass, and then we're going to talk about how to find the number of moles and the number of atoms. Still staying with this conversion factor concept. So has anybody gotten far enough in the course or remember from a previous course or have a guess about how we might find the molar mass of something? Which notice I wrote out the whole formula for acetic acid there, right? CH, there's 3 H's, COOH, and another H over here. And if no one knows yet, that's fine. That's why we're going to talk about it now, because this is going to come up. Okay, so this is one of those handy dandy times that we use a periodic table. You can use any periodic table that's accurate. I personally would recommend that you print one because they are incredibly helpful to use for this course. You actually will use a periodic table in this course. Now, what we do to find our molar mass is we need to add up how many of each element there are, and we just look at its mass on the periodic table. So for example, carbon, if we go to our periodic table, I have a lot of tabs open, I know, I have a tab closing issue, I like to have everything open, and we find carbon, right? We see carbon's mass is 12.011. In this case, we'll not round, but in other cases, you may end up rounding. So we know carbon is 12.001. How many carbons do we have in this molecule? Two, right? It might seem obvious, but we have one here and one here. So we have to count both of those carbons. So we're going to do 2 times 12.00, was it 011? I think so. Because we have 2 carbons, right? So that takes care of our carbons. Now we're going to do the same thing for our hydrogens. Well, how many hydrogens do we have? 1, 2, 3, 4. We have 4. So now we need to find out what the mass of one hydrogen is so that we can multiply it by 4 to find out how many are in acetic acid. So in this case, I hate how Zoom doesn't know what I want to click on. Okay, we go to hydrogen, same thing. We just look at its mass on the periodic table. It's 1.008. So we would write, maybe, 1.008 for our hydrogens, and then our final element in our compound is oxygen. And how many oxygens do we see? Two. We look up the mass of oxygen on the periodic table, and we see that it's 15.999. So we will be putting 15.999 in there. Okay, now we just add all those things up. So I'm going to let you guys try to do this math with me, and then we're just going to summarize and review exactly how I did that. All right. So see if you can get the same answer as me. Go ahead and try to figure out what the molar mass of acetic acid is. Oh, I'm sorry. I didn't realize my 15.999 kind of went off the page there a little bit. Does anyone have an answer? Thank you, Vitali. I got the same exact thing as you, 60.052. That's the molar mass of acetic acid. So to recap, all you do is you'll always be given the formula, right? Never in this class will I say, what is acetic acid? And you just have to know, right? Of course not. You look at the formula, you literally count how many of each element there are, you look up the mass of that element according to the periodic table, and you count it. So you could have written this out like 12.011 plus 12.011 plus 1.008 plus 1.008, right? You could have written it out for each one. I like to condense it like this because it's just easier to calculate. But there's no reason that you can't write each one out. So let's try one more before we go into this moles and atoms conversation. You try by yourself to find the molar mass of hydrogen peroxide, H2O2. So 2 H's, 2 O's. Those are subscript 2's, by the way. I wish it was just easy for the computer to know what I wanted, but it's not. So take a second right now, see if you can figure out what the molar mass of H2O2 is. Same exact concept we just did. In fact, I will leave the periodic table open for you in case you don't have one open. So again, that formula was H2O2. Great job, Logan. I got the same thing as you, 34.014, right? All I did was say oxygen is 15.999, times that by 2 because there's 2 oxygens. And then I added 2 hydrogens, which are each 1.008. So once you add all of those things together, you should get 34.014. All right, type a 1 in the chat if you're feeling pretty good about that. You understand how to find molar mass, or you at least know what it is. Okay, got 2 1s. Hopefully I'll get 2 more. But regardless, we're gonna go over this again, right? So if you're feeling a little fuzzy on it, it's fine. But all you really have to do is use the periodic table, and it makes it so easy. Sometimes people forget that step. Okay, so now that we know that, we're going to figure out how many moles are in a 5-gram sample of acetic acid. Now, I didn't tell you about units. What units does a molar mass have? Well, what was our molar mass for acetic acid? It was 60.052. The units on the molar mass are grams per mole. Now, it does not say that on the periodic table, right? It actually says like some like micro unit thing. No, it is grams per mole from the periodic table if you use the periodic table. So molar mass always has the same units, grams per mole. So now we can use that to convert for our 5-gram sample. So we're going to do some dimensional analysis. I know you thought we were done with it. Never. Right table. So we're going to start with what we know, which is that we have 5 grams of acetic acid. That's what we know from the question, right? They want to know how many moles are in that. All we do is use the conversion that we just figured out, putting grams on the bottom, 60.052 grams per 1 mole. Now, if we do our math and cancel out our units, we will be left with just moles, right? And grams will go away. I could have written acetic acid here. So does somebody want to do that math for us and tell us how many moles of acetic acid that is? Should be a pretty small number. Not that small, but small. Okay, Logan says 0.083. Sounds good to me, right? It should have been 5 divided by 60.052. Seems about right. So we have, if we had 5 grams of acetic acid, which by the way is vinegar, we would have 0.083 moles. Okay, now how many atoms is that? I'm going to give you another conversion, and I'm going to leave you for a second to try to figure this out. I'm not going to help you because I actually kind of have to use the bathroom, so I will be right back. But another conversion that you need to use is 6.022 times 10 to the 23rd power atoms are in 1 mole. That is called Avogadro's number, right? It sounds kind of like avocado, but it's Avogadro. He did a bunch of testing to figure that out. So that's how many atoms are in 1 mole. So knowing how many moles we have, see if you can figure out how many atoms. And actually, you know what? I'm almost done, so I'm just going to wait. So I'm going to give you a minute right now to try to see if you can figure out how many atoms are in this sample. Okay. I was trying to figure out how on my iPhone to type that in, but I just figured it out. Let's see. Logan got 5 times 10 to the 22. Yes, right? Especially if you round. Yeah, once I typed this into my calculator, I actually got, as my full number without any rounding, I got 4.99826 times 10 to the 22. If you're not sure how to type in those big numbers on your calculator, right? If you're using a phone calculator, you can take it sideways to get a billion more options. And the button that says, my phone is sleeping, that's why you can't see it. The button that says X to the Y will help you actually put in an exponent. So you can type 6.022 X to the Y button 23 because it's for the 23rd power. And then your calculator will actually write that out as a scientific number, right? If you don't have a scientific calculator for this class, I would recommend getting one if you can, right? It will make it easier. Plus, if you're taking this class, I assume you have some interest in science, right? You might end up using it later on in your life as well. So the answer is 5 times 10 to the 22, right? That's totally fine. 4.99826 times 10 to the 22, whatever you want to say, because we haven't really talked about rounding, but we're about to talk about it. So last little bit of stuff, we're going to finally say goodbye to dimensional analysis. Yeah, 5 hextillion, exactly, right? Really small. And again, that makes sense because atoms are tiny, right? So really a huge number of atoms are going to be in the tiniest sample of anything. Even if it was 0.00001 grams, there's still going to be a lot of atoms. So now we're going to talk about sig fig rules. This is something that a lot of people felt good on, but I thought I would just review, right? So let's see if you guys can say how many sig figs are in these situations. So this first example, 0.000000001, how many sig figs are there? Good guess by Oliver. So this one's kind of a trick. The answer is 1. Anytime that you have zeros that don't have numbers on both sides, right? So they're not sandwiched. These leading zeros are not significant. So I could have 0.0, I could have 100 zeros, and it wouldn't matter. None of those zeros are significant, only that one is. It's a weird sig fig thing, but it's the truth. So then knowing that, what about in this second example? How many sig figs would be in the second example? Are there 4 zeros? Yep, 6, right? Because in this case, the zeros are in between 2 numbers. They're sandwiched. They're all significant. But again, this leading 0 over here, that one is not significant, right? It's never significant in any situation unless there's a number in front of it. And then what about in this last example? 9, right? Same concept. The zeros are sandwiched, so they are significant. So really, for me at least, the trickiest one are these numbers with the leading zeros, because you think, but wouldn't they be significant because those decimal places are important? Well, they are important, right? But that's the rule. They do not count as being significant. So now what about if we're doing math? Right, because obviously we're going to do math with these numbers. Usually we don't just have one number. We need to be multiplying or dividing or adding or something. So let's say we take 7.5 and we times it by 3.44450091110. Well, one of these numbers has quite a few significant figures. The other one doesn't. How many do we put in the answer? And why, most importantly? But how many do you think we put in the answer? I hope everyone's going, some, right? So the correct answer is you would put 2 significant figures. You always take the one with the least. Good. Perfect. Perfect answer from Logan, because it's only certainly accurate to the second digit. Exactly. Right? It's like you're taking something that's not that accurate and something that's super, super accurate. Well, the thing that's not accurate is never going to become more accurate. You can't just add extra digits to it. So you always go with the least amount of sig figs, which is nice because then in this case, you only have to have 2. So keep that in mind. Anytime you're adding, subtracting, multiplying, dividing, you always want to go with the least amount of sig figs because that's going to help you stay more accurate. Okay. That was my little sig fig speech. Now, this other thing, most people got this right, so I'm not going to go over it about measuring with sig figs. We might go over that more in the future. But for now, what we're going to do is we're going to do the Module 1 DBA. So I'm going to go ahead and send you this link. I want you to open it. I've given you editing rights, and I've given you 3 questions here from the first module. And to get credit for the DBA today, all you have to do is put your name in one of the name boxes and then provide some answers to your questions. So you're going to talk about the difference between accuracy and precision. What is a mole? How do you find molar mass, which we just did? And what was the most important thing that you learned from this module? So I'm going to give you guys I'm going to say at least a minute right now where I'm going to just be completely silent, and I want you focusing on answering these questions. Feel free to use your notes, your resources, right? Anything that you'd like. And then in about a minute, I'm going to come back and actually start talking about what people wrote and giving some suggestions. Okay, great. I see a few answers already getting populated in there. I'm sure some people are still looking things up, right? And if you haven't completed the module yet because you're kind of new to the class, you can always go back in here and do this when you're ready if you haven't finished yet. That's totally fine. So don't feel pressured if you're like, I don't know any of this. You might not have finished the module yet. So let's see. We've got Oliver telling us that precision uses the accepted value for something while accuracy requires multiple values. Nice. You find out how many atoms they weigh. Okay, by adding the weight of all the atoms together. Good. Oh, I like what Chris wrote here. Accuracy is the closeness of a measurement. I like how Logan is just going to copy paste something I'm guessing from his notes. Accuracy describes the difference between the measurement and the part's actual value, while precision describes the variation you see. Yeah, so sometimes you see this described as like throwing darts, right? Where precision would be, are you throwing the dart to the same place each time? Maybe you're completely off from the bullseye, but you are constantly getting it in the same spot. That would mean you're very precise. Accuracy would be, how close are you getting to the bullseye, right? Are you getting a dead center bullseye throw each time? Great, right? Then you're being really accurate. Whereas you can still be precise without being accurate, because you might be throwing darts that are all going to the same area, but they're not near where you want to be, if that makes sense. But I find that to be a helpful way to think about it, is that you can be precise without being accurate, which is part of the flaw in science, honestly. All right. And I want you guys to continue writing in the document, right? To turn in your DBA, you can submit a link to this document. You can also just say, I attended the live lesson, right? And I'm going to go in and put a grade for you. But I'm going to end this session now just because in a few minutes I have my biology one starting, and I want to make sure that I have time to get that set up. So just spend the next couple minutes finishing this out, right? Or feel free to come back to it later. Totally fine. Otherwise, great job today, everyone. I hope that you have a little more clarity on unit conversions, how to set dimensional analysis questions up, and a little bit of sig fig stuff. Otherwise, I will see you guys next week.